Hi everyone, and welcome to my third sequential circuit video. In this one we are making a gumball machine that will spit out a random gumball once the user has input 15 cents into the machine, and they can only input nickels. And so in this video we'll kind of go over how that circuit works, and I'll show you the design process that I took in order to design ultimately the circuit on the screen here. And so what I did first was I created a state diagram. I use Figma in order to do that, just like a design app. And what I determined is that we need 3 different states only. I'm calling them A, B, and C. And yeah, so the first one is going to be A. That's going to be when and because we have 3 states, we need to use 2 binary numbers. And so we're going to have a 4th state that we're going to have to implement into our K-maps later, and I'll go ahead and explain that as well. But that's why we have 2 different numbers here. So we have state 1, or state A, which is represented by 0, 0. And that's going to be when there are 0 cents in the machine. And so basically what happens is that whenever somebody inputs a nickel into the machine, that's signified by our input is equal to 1, and then it'll take us to state B, which is that there are now 5 cents in the machine. And if they don't do anything to the machine, then it just goes back to itself. And so say that they've input a nickel, it's like, okay, well, and then same here. So whenever they input a nickel, it's going to go to there being 10 cents in the machine. If they do nothing, well, then it just goes back to there being 5 cents in the machine. And then for this one, this is where it's interesting because we don't actually have a 15-cent slot, which represents, the number of cents that you need in order to get a gumball. So instead what we do is we say, well, if they do nothing, then obviously it just goes back on itself. But if they do something, then, well, it's going to go to 0 cents, and it produces this star. And that star it's going to give them a gumball. And because we... the reason that we don't need a state for 15 cents is that, well, the circuit is over once they've input 15 cents. So once there are 15 cents in the machine, if we had an extra state that represented that, well, it's not like when they input 1 cent, it's going to go to 20 cents or something. No, it's just going to go back to 5 cents. And if they do nothing, well, it would go to 0 cents. So it's doing the exact same thing that A is already doing. So we could have a 4th state, but it would just be completely redundant and it would serve 0 purpose. And so we actually only need 3 states, which makes ultimately it makes the circuit more simple. And so I started off by making this state diagram here, and then with this state diagram, I created well, let's see here. I created this next state table, but I also had to choose a transition table, and I just chose well, in this assignment we were instructed to use a T flip-flop, so I just chose this T transition table here. And with this transition table as well as the state diagram, I created this next state table using Excel. And this basically is what I used to then come up with my Boolean equations for my different t values, because in a t transition table there's only 2 possible states for t, or there's only 1 variable rather, so it's either 0 or 1, and so it makes it very simple. We have a t1 and a t0 because we have 2 our states are represented by 2 bits, and so we need to be able to manipulate both of those bits. And so we have, T1 and T0, and then T1 and T0 obviously only have 2 possible values, either 0 or 1. And so I guess I could just give like a couple examples. So in the T flip-flop, we have Q of T and Q of T plus 1. So it's either, so you could say Q1 is equal to QT, and then Q1 from the next table is equal to QT plus 1. And it is, so if Qt is 0 and Qt plus 1 is 0, then T is 0. And so forth, and so, and then, et cetera down the chart. And so, we can look at the first one. Q1 is 0. Q Q I guess QT is 0. QT plus 1 is 0. So T1 is 0. And yeah, so we just say like when when x is equal to 1, which is when a gumball is put in, or a nickel is put into the machine. Say that there are 0 cents in the machine, which is represented by our state A. Then our next state is going to be B. And we're not going to give them a gumball. And by using that kind of logic, we eventually get to the point where they say, okay, well, if they're in state C, which is that they're 10 cents in the machine, and they put in a nickel, we're going to go back to state A, but we're also going to give them a gumball. And so that's what the Z represents. Is Z equals, we're going to give them a gumball. And then the T1 and T0 is, are we changing either Q1 or Q0 based on which state we're going to, depending on what X is. And so by using this next state table, I was able to create these 2 K-maps. Now, typically we would need 3 K-maps for this kind of machine, but the fact that there's only one possible state that the machine can be in to get Z makes it so that the equation is so simple that I don't even need a K-map. But for T1 and T0, I did need a K-map because there are multiple different states in which these are high or low. And so I had originally said that there were only 3 possible states for Q1 and Q0. I didn't include this 1, but then I realized that, well, my equations were wrong. And I pondered and pondered, and I realized, oh, well, because these are these 2 bits can be represented by 4 different possible states, well, I need to include these include 1, which is never going to happen on our table, or in our circuit, which is why we don't care. But we do need to include them when it comes to making the equations. And so for T1, I said by creating K-map, and this is a sum of products equation. So we're complementing it when our variables are 0, and we're not complementing when they're 1. So T1 is equal to Q0 and X, or Q1 and X, and T0 is equal to Q1, not Q1, and X. Or the complement of Q1, I guess you could say. And then for Z, since there's just one possible state, we can just look at the table and say, well, it's equal to Q1 and not Q0 and X. And that's it. So I didn't even have to make a K-map for that. And ultimately, that left me with this circuit here. Let me make sure I have the instructions here. And ultimately, that left me with this circuit here, which is I created. So this is T1. I created this circuit via the equations that we had. So it's Q1. Let's see here. Did I do that right? Make sure I did. Yep, I did that right. So it's Q1 and X, or X and Q0 is equal to T1, and then so on and so forth for T0. And I made Z down here via the equation that I didn't even have to make a K-map for. I just kind of come up with, which is Q1 and not Q0 and X equals Z. And then I just made the circuit here. So this is my clock right here. Perhaps I should label that. And so this is our flip-flop 0. This is our flip-flop 1. So for flip-flop 0, T0 is plugged into it. And since T0 is just equal to this equation here, we can use tunnels and just kind of plug it in. And then same for T1, and then same for Z. And so basically what it looks like, and this is a positively edge-triggered flip-flops. And then we have a... what's it called? What is that called? Oh, it's strobed. It's strobed so that our state is left up for a clock pulse after the state changes at the end there. So we can just kind of demonstrate it functioning. So when Q is equal to 0, as in a nickel is not input into the machine, well, whatever state it's in, it's going to stay in. So... and it doesn't continue to output gumballs over and over again. So it only outputs the gumball one time. So we can actually make it 1 and do a couple sequences, and then say that, okay, so we are in. There are currently 5 cents in the machine because That's what 0 or you read it from right to left, I guess. So it'd be 0, 1 represents. And if we're not putting any more money into the machine, well, it's just not doing anything. But then if we say that we put in a gumball or we put in a nickel, then it's okay. So this is positively as triggered. So when I click this, it's gonna change from it's gonna go 0, 1, 0, 1. Okay, and say that we input another gumball, or actually not a gumball. I keep saying gumball, nickel. Say that okay, we're at 10 cents now. Let's say we're not putting in a nickel. Well, nothing's happening exactly as it should be. Now, say that we decide, okay, well, we're finally gonna finish paying. Well, once I click this, then we're gonna be back to 0, 0, and because this is negatively it's triggered, it's going to return 1 once I click it. Once it goes back down. Or wait a minute. Make sure this is working right. So that's going to 1, and then we go down. Boom, that's 1. Go down. And just I think this weird discrepancy is just coming from the fact that it's strobed. But if we go up again, it's almost doing it early. But now we're at 0, 0, and it's 1. So it's just because it's strobed. It's just a little bit. It's like 1 clock pulse off, but that's normal. So I think it's actually working normally. Just a little bit of a hiccup. And so yeah, that's the circuit. And lastly, just explaining why this is a Mealy machine and not a Moore machine, and it's because X is in our it's part of Z here. So if this was a Moore machine, so X is our current input. It's like whether or not we're putting in a nickel. And if this was a Moore machine, well, X wouldn't be part of Z, and Z is ultimately what our output is. But if it was a Moore machine, or since it's a Mealy machine, it does have the X here. If it's a Moore machine, X wouldn't be here. And that's the definition of a Mealy machine. A Mealy machine uses previous inputs and current inputs to determine the output, whereas a Moore machine uses only previous inputs to determine the output. So yeah, that's all for this video. Thank you for watching, and we'll see you in the next one. Thank you. Bye-bye.